The universe has hundreds of billions of stars, so how many civilizations should exist right now? How many communicating civilizations exist? This is part 3 of our series, the Drake equation. In part 1 we asked the Fermi paradox, where is everybody? In part 2 we explored the Great Filter. Today, the Drake equation, the tool scientists use to turn a mystery into a set of questions. The Drake equation doesn't spit out a fact, it breaks one impossible question into smaller testable questions. It's a flashlight, not a crystal ball. It organizes our ignorance, showing what we know, what we think we know, and what remains mysterious. Frank Drake created it in 1961 to guide a scientific search. SETI. Each factor is a piece, from the birth of stars to the longevity of civilizations. Conceptually, it asks, how many communicating civilizations exist in our galaxy right now? Communicating is key, detectable signs, radio, lasers, even industrial heat or pollution. Each term is a filter, narrowing from all stars to the few we might actually hear. We start with stars and apply fractions for planets, life, intelligence, technology, and time. It's a logical progression. Let's walk through the steps together. And remember, it's a range, not a number. Uncertainty is the point. The first term, our star, asks, what's the average rate of star formation in our galaxy? We care most about stable, long-lived, sun-like stars. Across wavelengths, telescopes peer into stellar nurseries to estimate the birth rate. Today's estimates, roughly 1 to 3 sun-like stars per year. Over billions of years, that adds up to vast potential homes. So the first filter isn't very restrictive. Our galaxy is fertile for stars. Next, what fraction of stars have planets? Kepler changed everything. By watching for tiny dips in starlight, Kepler found thousands of worlds. Planets are the rule. Most stars, maybe nearly all, have them. Here's the surprise. Planets are the easy part. The discovery shifted the conversation. The galaxy is teeming with worlds. Third, the average number of planets per system with environments suitable for life. The habitable zone. Not too hot, not too cold, so liquid water can exist on the surface. Water is an excellent solvent that enables complex chemistry. While estimates differ, Kepler and other missions suggest many Earth-sized worlds in habitable zones. As an illustration, perhaps about 1 in 5 sun-like stars could host such a planet. So the first 3 terms now point to a universe filled with promising real estate. Planets were once the big unknown, now they're the easiest part of the equation. Fourth, on eligible planets, what fraction actually develops life? Abiogenesis is a monumental mystery. It happened at least once here, perhaps early, soon after conditions stabilized. That single data point can be read 2 ways. Life could be easy, or we just got lucky. Optimist. Given the right ingredients, life is a cosmic imperative. Pessimist. The leap to self-replication could be astronomically rare. We don't know. Fifth, on worlds with life, what fraction evolves intelligence? For most of Earth's history, microbes ruled. Complex multicellular life is recent. Human-level intelligence arose once, very late. Evolution doesn't guarantee telescopes. Many successful species never build technology. Is intelligence a powerful, inevitable advantage, or a rare convergence of pressures and luck? The universe could be full of life, mostly simple, microbial, or uninterested in abstract technology. These 2 steps are enormous hurdles, and they dominate the uncertainty. Even with intelligence, a species isn't counted unless it becomes detectable. We search for techno-signatures, radio, lasers, industrial imbalances, even heat from technology. SETI began with radio. Civilizations might use or leak powerful radio signals. Earth has leaked broadcasts for about a century, a tiny, faint bubble. We're expanding the search. Lasers, unusual transits, and atmospheric chemistry only tech can produce. We're limited by our own lens. We tend to look for things that resemble us. Some intelligences may choose low-impact lives that leave no detectable trace. Finally, L. The length of time a civilization remains detectable. This single variable can multiply n to the skies or collapse it. If civilizations are fleeting, our brief window might never overlap with theirs. Long L. The galaxy flickers with signals. Short L. It looks mostly dark. LE could be short if civilizations self-destruct, face environmental collapse, or move beyond leaky tech. Or long if they achieve stability, efficiency, and sustainable, durable technology. Silence may mean we're listening between fireworks. between eras when civilizations are loud. Let's compare two plausible ranges, without pretending certainty. Optimist, life arises often, intelligence is advantageous, technology emerges, and L is long. Pessimist, one or more steps are rare, and L is short. Outcomes range from neighbors within a few hundred light years to a galaxy where we're effectively alone right now. Two people can use the same equation and get answers that differ by millions. Uncertainty isn't a flaw, it's the point. The equation frames what we need to learn. If Drake says civilizations could exist, Fermi asks why we don't see them, and the Great Filter asks what stops them. So the Drake equation doesn't answer, are we alone? It asks, which step is rare, and how long does a civilization last? Is the universe quiet because life is rare? Or, Huan's, civilizations don't stay loud for long. Watch part 1, the Fermi paradox, next, and tell me, which term do you think is the hardest?
Thank you for watching. Please subscribe to the Off the Chart Multimedia YouTube channel for more fascinating videos.